I'm Chris Ryan. We'll get into a little bit more who I am in a few minutes. But why we're here, design patterns. Design patterns are a secret code you've probably heard your coworkers talking about, where they talk in these secret, strange words, and they're talking about different design patterns. Observer, visitor, yada, yada. And it's a secret for a reason. There's a secret handshake that goes with it. However, I'm not allowed to share that with you. So, design patterns are something that we can use to communicate to each other really quick ideas of how our application modules are going to fit together, how you pass data from one to the other, how the glue that goes between them. Design patterns are not code, they're not architecture, they're not a design. A crude word form is a template, but that's overused in C++. Design patterns are not only for C++, and they're not only for object-oriented design. They're just something that, once you get to know these patterns, it's something that you can see in code that will just kind of stand out at you. The other thing is there's a lot of symmetry between different design patterns where in mathematics or physics, you come up with a postulate or theory, or actually even better, geometry. The two-column proofs you had to learn in junior high, where you came up with a few different base ideas, you would come up and build extrapolated ideas and theorems off of those. Design patterns are kind of like that. Once you've got a base set of design patterns, you can take those and extrapolate them to fit in your design. They're relatively well tested, and so they're uniform concepts. So I will give you a little bit of a warning. This is a back to basics talk. If you're advanced in engineering, you might find some of it boring. Everything I'm doing is C++ 11 compliant. Design patterns originally started in the 90s, so pre-98. So nothing in there requires all the new fancy bells and whistles. You don't have to be using C++ 17 or 20 or 23 to get the latest and greatest features to do any of these things. These are just rough cut ideas. Who am I? I'm a guy, just any old guy, just like any of you, not a software god. Classically trained in software engineering and hardware. I specialize in modern C++. However, I've used a ton of languages over the years. C++ is my favorite. You know what you like and you like what you know. I've worked in a lot of different complex problem spaces. However, I dislike complexity. I reduce and make things simple. If the code is simple for you to read, it's simple for the compiler to read and easier to optimize. Pet peeve, don't pre-optimize things, you just get in the way of the compiler. I do really small projects in firmware and embedded, which I'm trying to put on hold because so many of that gets shoved into a C world, not anti-C, but it was degrading my C++ skills. Recently joined the ISO committee so I can cause trouble for all of you guys. And personal, more biased peeve, I don't like C# and .NET, two monstrosities, or any of the Java, JS, BS. Design patterns have a lot of benefits. So you can speed up development by improving testing and yada, yada. A lot of people criticize design patterns that they say, well, you have to use this design pattern because your language is incomplete and can't do all these things that all these other languages can do. And if you're trying to do something that doesn't fit well into your language, you're using it wrong. If you're going to be designing something, it should be simple and easy to use. If you misuse patterns, it becomes an anti-pattern, and which then interferes with development. For example, maybe many of you have heard of singletons or an anti-pattern. If you use them wrong, they basically become a big global variable. That's the wrong use for them. A singleton should be something that has a single instance where anybody can get at it, logging engines, for example. Okay, so a lot of people, and I bet every single one of you has a notepad or .text file on your desktop where when you find something you like, you cut and paste it into there so you can go back and find it later. Say, I know I'm going to use that. I found it useful. I'm going to do it again. Throughout history of software development, people have done that. They make their own copies of code they like or some algorithm, and they save that. That's their personal toolbox. Over the years, people started to share their personal toolbox and found that that is something that they needed a common language to talk about these things. In the mid-70s, Christopher Alexander started doing design patterns. He's not a software engineer. He didn't touch software. He's an architect. He laid out patterns of what cities would look like, streets and buildings, and all the way down to what is the best or a way to describe windows in the building. Much later, a bit later, a group known as the Gang of Four, GOF, designed some software around these concepts and named these patterns. There's 23, some of them, really 6 or 7, and others are extrapolations of those, special cases. Actually, just slightly before them, with Steve McConnell did a book, Code Complete, where he also talked about patterns without calling them patterns. Over the years, other people, pattern-oriented software architecture, there's 5 volumes that came out over the years. Each one had 4 or 5 different authors. They collaborated on different ideas. The latter books got more specialized. Some were more database-specific type technologies or designs and architecture. But they're pretty fancy, they're standard books you can find, and people may reference them at times. I'm primarily going to talk just about the original Gang of Four and some extrapolations off of those. Software design patterns are not the full big picture architecture. Where's my dot? Come on, wake up. Sorry. We're going to walk it from one screen to the other. Architecture is the whole system, how the whole thing fits together. Some of these have architecture patterns, client server, microservices, frameworks. And then there's implementation, which is actual code. That's not design patterns either, but there are implementation patterns there. There's idioms, classes, structs, virtual mechanisms. Those have design patterns. Those are not software design patterns. Those are like visitor strategy, object, or polymorphic. Those are a very thin layer of interface between the big picture architecture and the implementation. This picture, I have to give proper credit, really, really small print in there. I stole from Klaus Eigenberger from his book. Klaus is a really good big picture architecture all the way down to the small level of design. This book, his that came out this last year, really good book. If you want to get into it, I recommend getting his. He teaches a lot of classes. He's written a ton of books. He also is a frequent speaker. Rainier Grimm's also has a whole ton of books across a lot of different languages. He also does a lot of tutorial instruction type stuff, some online, some in person. Good speaker. And he actually has a series of mentoring programs of working people through that. Look both of them up. Good people to follow. Rainier is much more active on social media and his web blog, constantly putting out new material. If you're on LinkedIn, follow him and his company, Modernness, C++. So, highly recommend both of them. In a lot of what I'm going to do here, the code you'll see on the screen, more of kind of a pseudocode, slideware, left out a lot of important words. Rather than actually saying like shared pointer, I just say pointer. It could be whatever pointer mechanism you want to use. The original design patterns were written using raw just asterisk pointers. I don't recommend that. Modern C++, we should be using managing pointers. And when I say make, that could be make unique, make shared, whatever, but it should be some managed mechanism for that. And then, of course, when you call off of that, it's just called method. The slideware gets a little sloppy of what is actually a pointer, what's not. It's just meant to give you the idea. Every slide that will have a Godbolt link on it. So when you get the slides later and you download them, you can take that direct link and see a code example. Most of these code examples are super lightweight. They don't really do much of anything, but they'll show how the different mechanisms fit together. And I said, this is C++ 11. And so it's something, I know a lot of you work in places where your bosses aren't ready to move to 14 or 17. So you're stuck 12 years in the past. Everything still works. 90% of what we do as software engineering in C++ is the core fundamentals that Strustrup originally put in the language, or kind of like the second generation of the language from the mid-70s. So what's there, or actually late 70s is when he designed it, but shortly after that. So you don't have to have all the latest bells and whistles to do everything you need. The base concepts are still the same base concepts. We didn't break anything. Okay, here's what a generic pattern will look like. Most things are based off of an abstract class. We may call that a pure, functions and that type of stuff. It doesn't have to be. It could just be a lightweight class that just has a base implementation, and then derived off of that has concrete classes. And my little arrows show relations. Coming this way shows when I've made an object. Going the other way shows when calls are made. When they drop down and hang and do a quick turn, that's a polymorphic call, or whatever technique you're using in your implementation. It doesn't have to be the virtual mechanism. It could be a static polymorphism. And then many of the patterns go from a interface that you have control of to one that you don't know what's in there, and where it provides you what the object is. You just have an interface to it, and it creates for you what it wants, and you can call off the base implementation, the method. And so my laser pointer isn't working right. So you make the object, you create the subordinate object, and then you call a method on it. This is how you're probably actually used to seeing this stuff in code typically. You have your main file, and you only have a header file that includes the header files from the other modules. And I'm gonna hate this laser pointer. The implementation is in a different directory. You don't have access to it. You only have the header files. And even this module doesn't have access to the source code development. It only has header files. Sometimes you have just the pure interface. Sometimes you actually have the class definition. Here, this guy can't actually create one of these. He has to call a function called create instance, and it makes one of these objects. Then it interrogates this object, and it makes one of these objects. Here, I actually make the actual instance here. I could have just as easily had a create instance to function here that this guy could have called and been entirely divorced from the implementation or the actual knowing of what the class was. So this box would have moved down, and the header file would have a create instance prototype the same way as this one would. I am open to interruptions if you have, if I'm saying something that's not making sense or you have questions about. So, of those slides we just saw, if you globbed them all into one file, this is what it would look like. In abstract class 1 and 2, I did them out of order so I could use the shared pointer of the abstract class for abstract 2 and just It reads pretty much exactly like you would expect. Regular polymorphic mechanism, make the shared, I call off of that, the create, and for class 2, and I call the method. The main only knows about the base interface, what would be in the header. Some of the patterns can be extended or use a concept of like daisy chaining things together or acting as filters. So when a call goes down the pipe to get to the other side, there's an intermediary handler or arbitrator, and it can decide to pass the call down through, or it can hijack and say, no, we don't want to process that now. Let's just send that back up with either an error code or you've cached it, or when you're passing things down, it can decide it wants to modify the parameters because it knows the target on the other side doesn't speak the same language as your program does or your module. So it massages the data, it massages it again, or it just passes it through. When the return values come back up, it can massage it again, or just pass it straight up. So if you kind of remember this concept, there's some of the patterns that we'll see which use an idea directly off of this, or you can extend a lot of the patterns to do this yourself. When I showed that previous code sample of where I just call a method in the secondary class that I didn't know anything about, the middle class could have actually hijacked that and massaged it and done what it wanted to do with it to adapt between them. Okay, a $25 term, which is really only worth about 5 cents. Some people really, really, really go out of their way to make it overly complex. Dependency injection. I presume a lot of you have heard of that. It's become a secondary pattern. Dependency injection means nothing other than your class has a dependency on other ones. You either do it polymorphically or do it via template mechanisms. So most of these things we're talking about when I talk about polymorphic could just as easily be compiled through temporalization and fixed that way as opposed to be a polymorphic runtime pass-in to it. But they both work very much similar to each other. In the polymorphic way, say we have a data source and a data destination. You're reading from a file and you're spitting it out to a network stream or vice versa and copying back and forth between them. Come on, point, where are you at? So you open the file, you open a stream, and you say, copy everything that's in the file to the stream. Your code doesn't know what it's talking to, and these files and streams are based off of a data source. And the data source itself only knows about how, basically everything a file would know about. Open, close, read, write, seek. And you can do a templatized version of that same thing where you say copy all and from a file to a stream, and the template comes in and says, source, we're gonna wanna read from the source, destination, we're gonna write to the destination. So you basically just have the template automatically figures out, says, there is a member function called read, I'm gonna call read. Polymorphically, when you do that, you have to have a base class, throw a virtual, go down to the read, and then the same interface is handled for the stream also. Because what would I do is just in this crude little sample, reads everything from the file, shoves it out on the stream, turns around, does a seek on the file, seek on the stream. Normally you can't seek a stream, I made that up. But then you read everything from the stream and you copy it back to the file. Here we do the exact same thing. No difference in the code other than this is a polymorphic call and this is templatized. This is smidgen faster because it's a direct call. But it's compile time dependent. Here, you could take and pass in, I happen to have this being a reference, but it could have been a pointer. Runtime can decide what it is you're gonna be passing it in, and your mainline wouldn't know. It could have been a stream copying to another stream. Over here, the compiler knows we're dealing with exactly these specific objects, or objects that fulfill the API of the read and the write. So we're going to talk about creational patterns, structural patterns, behavioral patterns, and as of late, there's become a new concept called concurrency patterns. We're not going to talk about those. Rainier has a whole series of blogs and stuff in his books that he talks about those. But basically, those deal with sharing data, mutation data, concurrent architectures, and concurrency is not the same thing as concurrency patterns. Those deal more with blocks of processes and threads. They're simultaneous and procedural. Concurrency means happening at the same time. Concurrency is not parallel processing. Parallel processing is actually everything truly happening at the same time. Threads and processes are serial. It's like a main line. Do this step, do this step, do this step. And you have to synchronize your two different steps going back and forth. So we need synchronization mechanisms. And then there's inter-process communication. How do you actually share that data? We're not going to be talking about those today. Okay, here's a different design pattern. Under creational, we have a whole set of different categories which create things. Your structural design patterns are how objects relate to each other. Behavioral is more internal to an object of what is its brain doing? How is it behaving? Why is it doing what it does? In creational patterns, you can ask to create abstract objects, or you build, or if you actually build things in a certain way. A factory, you can ask some other module, give me a factory that will make something for me. You may be talking to a plugin manager and says, give me a handle to a filter that I can then pipe data through to save data out on a network. And it could be using, you could say, I need just type of encryption or this type of encryption. And you don't really care what it is. The module knows how to give one of those to you that you can then use. And you don't care what that module, what it is it gives you. You just basically have an abstract interface, and internal to that object, it deals with the concrete object. Oops, I should actually explain the others a little more. Prototype is a fancy term for saying, okay, interview question, you always get, define what a virtual function is. You can have a virtual destructor. What is a virtual constructor? There is no such thing as a virtual constructor. But if you have an object or a base implementation or a base pointer to an object, you can ask the object to copy itself. That's all prototype is it clones itself for you. And then a singleton is a single object data repository global interface. Like I mentioned, logging engines. That no matter where you're at in your program, you say, I need to log something. And you just call this API and it does it. It handles mechanisms for synchronizing and merging that data if they're coming from different threads. You don't care. It just packets your data and saves it away for you. You don't know if it's saving it to a text file, out on a network stream, to a database. Let that object decide it. But that's your one mechanism for finding it kind of anywhere in the world. Structural, like I said, is the how things fit together relationship to each other. And these are ways of kludging and gluing these together. Adapters, if you have a class that wants to write to sockets, but your implementation of sockets speaks a different language. You're on Windows and you're using WinSock, but you want to use a BSD sockets. I actually had to do this in a project that was platform independent of whatever we were writing for. We had our own socket interface and whatever was available on that platform. We adapted each interface to speak the language of either BSD or WinSock The error messages are different. The parameters going into them are different. The adapter munged the data on the way down, chained together like I showed in the previous diagram, and then the return values on the way back up, massaged them. So our base socket library could work the same no matter what platform we were on. Bridge, kind of similar idea, but it's a little bit more abstract. The going to need to get into some more examples so you can see more of what some of these are later. Composite is you have a bunch of objects you really all want to treat as if it's one object. So you have, for example, drawing objects. You got a collection of them and you say, I want to make them all red. So you basically tell your one object, say, make the objects red. And it goes through and enumerates through the children under it, and it knows how to handle that for each of them. Decorator is like that daisy chain we were talking about before. When you make the calls down, it acts as a filter and munges the data as appropriate if it knows how to handle it and passes it on down. Facade is very much like composite, but it's a simplified API where you just say, make me something that, does one of these, and internally it actually takes a bunch of different APIs to do that same thing, or to collectively do all of the big steps. It takes care of all the mundane small details. Flyweight almost should be in Creational because a lot of implementations of that use a class factory in that, and then it caches the implementation of that. So once you have one of these objects, then you can just ask this object to do something. Again, it has its own state, but it almost acts like a stateless interface because your parameters that you pass in are going to be handled and processed and passed through. So you're one object that has all this state, maybe a database interface or something, but it knows how to pass these through without affecting the current state of what your current connections, whatnot are. A proxy is a placeholder for another object. It basically is an adapter in the middle, but it might be talking to something on a foreign machine somewhere else. It might have some authentication mechanism in there that the very first time it establishes the connection. It's basically used to reduce complexity between what's here and there. It might actually also act, especially if you're going to send it to a foreign machine across the wire, it may actually bundle up these data and cache them and tell it, you actually want to do a transactional commit, and then it sends them all across at once. As far as your program knows, it did its things and it wrote them. And the proxy is holding on to these until it flushes. Behavioral, I'm going to try and speed through most of these. Chain of responsibility is one of these daisy chain type of things. Delegates the commands through a cascading filters. Command is another caching mechanism where you say, I'm going to do this and this and this and this, and then you say execute. Interpreter, it says it implements a specialized language. The example I have in here is actually a bad one, not a bad one, but it has a hierarchical mathematical equation, and then I just tell it to evaluate it, and it executes it, and it calculates the answer. You're probably more familiar with something along this of a database connector where you give it some crude SQL command, and it processes that or executes it and munges it and then executes it. Another one is a regex expression. Regex is its own language, has its own processor, and you say, here's the string I want you to evaluate, and it gives you back the terms. It knows how to dynamically figure out all these different terms based on what your actual expression is of what you want to parse. I'm going to do this next one out of order. Observer is a publish subscribe. Someone's pushing out data, and everybody who is subscribed to it is listening to it. It's like your newspaper. There's a publisher of a newspaper, and you subscribe it, and the paper boy delivers it to you. In the observer pattern, everybody gets a copy of it because they all send their messages to the newspaper, and it's the want ads, and then you put a posting in the want ads, and everybody gets a copy of that. The mediator is like that, except for you never see your own ads you post in the newspaper. It's redundant. You shouldn't really care about it. Observer and mediator could be like a chat program where you send out general broadcasts. You don't care what you said. You already know what it said. I skipped iterator. Iterator is very much like the C++ iterators we're familiar with. You have an object that has a collection of data and you want to go through them. You don't care what the implementation is underneath. State is normally you've seen like state machines that have the big event-driven switch statement in them. They each have the particular state they're in, and events come in. They can trigger them to change between different states. I'm actually going to show you another weird version of it where the state is actually an entire object that polymorphically can change based on the event that comes in. It can decide which state you're going to be in by creating a new object and assigning that back. Strategy is switch algorithms on the fly at runtime. That could be your encryption algorithm. If you have your network socket and you're writing data out, and you decide, well, at this point, we're just going to do plain text, and you're doing your stuff, and then you say, well, we now need to encrypt this data, so then you plug in some encryption into the socket, and it's going to now write all this data encrypted. Multiple template, we'll talk more about that. Visitor is probably one you've seen a lot and used a lot and didn't realize it. If you have a tree structure and you need to walk the tree and do something to every node in the tree, a lot of you say, I've never done that. If you ever had a tree structure and you want to go spit it out to a see out, you traverse through the tree and you tell each node, spit yourself out. And it streams itself out to see out. And then it goes to the left branch and the right branch. And while it's doing the left branch, recursively going down, me left, right, me left, right. And it traverses through them all and it spits it out. So that's what a visitor is. It visits every node and it gives that node an archive object or a stream, an out stream, which is see out, and it just saves the data to it. Doesn't matter what it is, the object knows how to stream itself out to that, and it handles itself. That's a visitor. You visited every node in the collection. It could be an array, it could be a tree. You don't care, your implementation knows how to handle it and how to traverse its data. Okay, creational patterns. The hand of God creating the earth. And we talked about this list here. Okay. Design patterns, each cluster of category has what it claims its benefits are. These are generic. Every good programmer says they want to create flexibility, maintainability, reusability, scalability, reduce code duplication, and increase performance. Pretty much each of the different categories says this. Some of them have some more adjectives they use on there. They're meaning the same things. The factory. You have a creator interface that what's an example here? If you have a middle tier and you're saying, I want to know how to do, or I want you to create me an object that knows how to create further objects that will do what I need to do. Say you have a word processor, and you load the word processor and you say, create me it's something that knows how to handle documents. And then you tell that guy, create me a blank document from a template, or create me a document that's a PDF, or it's a Word, or it's an HTML type document. You only basically just asked for an interface to your middle layer that said, create me a factory, and then you ask your factory for, create me a product that does one of these. You don't know what the factory is giving you, the middle tier here, of how that works and what it's doing. You're just saying, I need a Word document. That knows how to go off and make a Word document, which is under a generic product. And each one of these know how to do that. And you get back a generic interface that knows how to add text to something or how to make it bold. It handles all the implementation. That you don't even really know what document type it is, and you don't care. I talked about the Godbolt links on everything. There's an example of that. That does a simple little crude program which does almost this example that we have here. Abstract factory is it's for objects that have groups or clusterings of like-related things. You ask for a factory and then that factory knows how to create multiple different types of documents. And each one of these factories talks to a different type of abstract product. Examples of that might be a UI theme, where you say, I want a dark interface. So it knows how to create you all the buttons that have a dark background and light foreground. You got radio buttons, static text, edit boxes. And so you talk to the abstract factor, to your middle tier, and say, give me something that knows how to create a dark object. And then you call it and say, make me one, radio button, make me a text box. And it goes off and it creates those for you. You don't really care what it is, you just know that it's a generic button or it's a radio button. And the same with the light factory, the light theme, it does its own thing for that. Other examples would be operating system components. A file system, for example, you can create files, you can create directories. You don't care what operating system or what file system you're on. You just know there's hierarchical structure of directories and files. You can do those same things here. Builder, this is a real common example. I hate it, but you have a cook in a kitchen. He directs how all his underlings how to make stuff. He says, we're going to make a pizza, and we're going to have these, I hate the term here, cookie cutter templates of, we're going to make a pizza. Every pizza's got to have a dough. It has to have a sauce. You have to have toppings on it. And so he says, you're building pepperoni pizzas today. You're building Hawaiians. So he goes off and he says, he gets his builder and he says, you're going to build the Hawaiians. You're going to put the ham and pineapple on it. I know some people hate pineapple. It's not that bad. So the cook director will say, okay, give me the dough that we want for your type. Give me the sauce that you need for your type, and put the toppings on there and return me the pizza. And it passes it back. So he delivers a Hawaiian form. He talks to the guy that's doing the spicy, and he's doing a pepperoni and sausage. I believe that's what that one's for, yeah. pepperoni and salami is what the example says here, but it's on a thin crust and it has a hot sauce. So it's the same steps, and you just basically have this subordinate object, go back, that knows how to build each of these things. So you have one controlling object that knows how to tell subordinate objects. This is basically, it's a recipe. Step 1, step 2, step 3. Each of the subordinate people know how to build their object of that type that fulfills the need that it has. A prototype, this is the clone. And this is a compound example here of you go off and you create a concrete object of prototype A, and then you get it set up the way you want, and you say, okay, clone yourself. And so now I have a copy of you. You say, why did you do that? I already have the original object. Why would I need a clone of that? Say you're doing a backup system, or a backup. You're gonna make a backup copy of where you're at, this snapshot. And you're gonna save that and go off and do a bunch more work, and you create another backup. You all of a sudden have an undo system. If you've made some mistake, you can just revert back to a previous copy. Sean Parent gives an example of when he was writing one of the Adobe products, they needed to put an undo in, and they were gonna track every single little step that happened and be able to figure out how to do and undo each one of those. And that was just a nightmare, pain and maintenance to put that in on every single command. What are your do and your undos for all these steps so they could play these forward and back? It's just a lot simpler. We'll just make an entire copy of our entire document and save a copy of it. You do a couple more steps, you save an entire copy of the document and save it off. So many times it's very quick to do that. Don't tell Sean I stole his example. Sometimes you may want to do this, and this kind of leverages into the flyweight pattern that we'll see later. You have an object that's really expensive to create, some database interface. And establishing the original connection to the database is really expensive and really slow. And all the authentication and the handshaking back and forth. So you have your database connector, and you say, okay, now I want another one of those interfaces that's already initialized that I can do a bunch of separate transactions on. You can just say, take the original interface and clone it for me. Use that as a prototype and give me 2 or 3 copies of it so I can do all kinds of different transactions. Your work has already been done on all the initialization, and this just uses that pre-done work in your new object, and so you don't have to reestablish all the connections. And it's easily disposable too, because you still have all your connection open. Okay, singleton. This is the old style of doing a singleton. We'll get more of what's into an actual singleton later. But prior to C++ 11, you couldn't create something and initialize it really at the same time. You had a static pointer that had to be outside the class, and you would say, well, if this is null, we'll go out and new it. That's perfectly fine. But different threads trying to do this at the same time of getting the singleton and it hadn't been created, you'll end up with 2 copies of it, and they'll write it back on top of each other. This new could be done simultaneously in 2 or 3 different threads. The last one in writes its instance to this instance pointer. You could put some synchronization mechanisms around it. Those are different on different platforms, dangerous, sloppy, potential race condition. After C++ 11, we have a static initializer. A static member in a function, if it gets called from multiple different threads at the same time, you are absolutely guaranteed only one of the threads, the first one there, will do the initialization for you. So we actually make a static copy of our instance of the singleton local to a function. And so whichever thread gets there first will do that. Anybody that needs that singleton later, that data from that, will call the static get instance function and just get a return the pointer to the data. That in many implementations, this data class is an internal class to the singleton. The outside world really doesn't even really need to know about it, other than what a generic interface is of show a message or set this property, or get what the property is. A case when you potentially want to use a singleton is configuration information of how you're going to set up your instance of your application. You use Visual Studio and you don't like the way it does the dangly curlies. If the auto indent, you change your options to say, I want the curly to be aligned, or I want 3 space tabs or 4 space tabs. It's a global option across everything. No matter what document gets created, or it's always going to use 3 space tabs or 4 space tabs or whatever you set. Another instance would be if this show message was a logging, you want to call your one global object and save some logging information. It can figure it out. You can have parameters in there of is it a warning or is it an error? It can decide what its filtering is and what messages it's going to throw out and which ones it's going to save. So you have one spot where all that resides. This is a variation on a singleton. I included it because it's well enough known. I absolutely detest it though. It is a global object that has static variables, and this is a really crude example of your object has a name and an age. There's a global, and anybody can call the get name on it, or anybody can call the set name on it, and they set what the name is. Sometime later, someone comes in and sets what the age on that is. And you're guaranteed, no matter where in your program this is called, there's only ever one instance of the data, and you can get at those. And this doesn't require actually spinning up a separate object the way the previous example of singleton is, where it actually creates one at some point in the future. They're just there. One benefit of the singletons, this is stepping back, this static data here is not created until it's actually used for the first time. It's the benefit of if you don't use it, you don't pay for it. That could be an expensive object to create. It could be your logging engine actually has a connection to a database and it stores away all your logs to a database. That can be really expensive to create. And so if you're never going to actually call that and use that, it doesn't have to create that interface. And it could be something that's really bulky in memory too. And if you don't use it, you don't pay for it. Okay, went the wrong way. Monostate, if your object here, I just use simple examples of a string and a number, your logging engine, and this object is created in global scope. So it's created before main. If it's a database connection, when you're waiting for your program to launch, you're going to be waiting 20, 30 seconds for your database to establish its connection and initialize all the memory, yada, yada for that. You don't want to do that. This is a sloppy way of doing something ahead of time. Okay, this is something which I've kind of come up on my own. This is a really stripped down, super narrow example of, and this is C++11, even though there's variadic mechanisms I'm using in here. I'm using standard function. I can say, I want to register a type with you that's going to use these parameters, and you can store that away for me. And later, and you can create hundreds of these things. And later, I'm going to call you, and I'm going to say, create me one of these, and it's going to use those parameters, and it's actually going to new it for you right on the fly and pass it back. The handy, tricky mechanism on that is I'm storing these away in a map. Come on, pointer, where'd you go? Oh. So I got a using where I'm going to have a map of a key. It's a pointer to a function which will return me a base pointer. And this function is actually this lambda here, which will make me shared of whatever my object is, and I'm going to pass in the parameters to create. So I actually call the create calls into map calls down to here, and map says, give me a reference back to this map object. And it's gonna say, find my key in there, and if it did find it, it wasn't at the end, I'm actually gonna call the map on that key and create it, passing in these parameters, which are then gonna pass into the lambda that I stored and create the object for me. Example of how I would want to use that. Say you have a whole bunch of different services you're going to be using, and you want them to be very lightweight. You can just generically call them later. You can register a bunch of different services and say, this class is A, I'm going to want to create an object called foo. Service B, I'm going to create an object called bar1, and it's going to use these parameters of extra. Service B, the same class of object, I'm going to call this bar2, and it's going to use the parameter data. I can then later come along and say, create me a foo, and then call this function do, which the service has built into it. Bar1 and bar2 are also going to create a service, they're both going to create service Bs and call the do on them, and it's going to do something based on their variation. These are one copy of these stored out in memory. Because this is templatized, that map that we had, back here, this whole class is templatized based off the base of what type it is. So we know that so this class has a function that's map of a factory of type base. So when I say I have a factory that is going to be handing out services, that's my base class, and this is the derived one that I've registered. I can later say, call that factory of service and create me these foos. That same templatized factory mechanism, I can do a factory of shapes. I register a circle. I just call that type 1, or square type 1, circle type 2, triangle type 3. I could have passed in or set it up so it did extra parameters and said, I want a red square, I want a blue square, I want a green triangle. And you registered these in this registry. And then later, you could have just said, without knowing how to actually create one of these for yourself, you could have just said, create me a red square, stored away a pointer to it, and then called it later and did whatever you wanted to with it. Here, I just haven't spit out their name. Most objects don't care what their names are. They more of care about what their attributes are, but that was just for this example. And you can mix these in the same program. This factory shape can live in the same program as the factory of the service. And it looks like they're storing them away in the same factory, but because this is a factory shape, is different factory service. Here, my quick example in that template is it was always, the default key is a string. Here I said, I want my key to be an int. So I just used an int. And it knows how to map it based off of that. This is the same slide we just saw before. The key defaults to a string unless I define it, and then it passes it in and it builds my map of that type. So this is not in design patterns. This is just something to make your mind think of what can I do with some of these, and also shows, even though C++ 11 was 12 years ago, it wasn't that primitive. You can do a lot of really fancy things that a lot of people, they look at that code and say, oh, that must be like 20 or 23, because you're doing all these really weird things. They got lambdas. I got standard functions. I got variadic arguments. Primitive isn't that primitive. Okay, structural. When you want to connect multiple different modules, that you build a bridge between them, and that's how you get there, from one side to the other. We've saw this list before. This is just the different ones that fit into there. Again, some of the adjectives they're using for why you'd want to use this. It creates abstraction and flexibility, reduces coupling, separation of processing. The algorithms are different from the structures. And improved extensibility, flexibility, performance, security. No one's going to ever advertise, say, degrade. These are just, you know. Okay, adapter. Basically saying, I want to use this type of object, but I don't really know how to talk to it, so I'm going to ask the adapter object that it knows how to talk to it to translate it. That network communications, I was talking about the socket protocols. I had my library, I had the different platforms I was on, translate and do this for me. You may use something like this if you're adaptee, you're going to wrap some old legacy code and you want to isolate that in its own module, but you got new code that knows how to speak its new flavor, but you need someone that translates between the two of them. That's what the adapter will do. It's also good if you're borrowing an open source library and you want to isolate that from the way that you do things and have it translate between there. It doesn't just have to be your old legacy. If you take that and multiply the previous adapter pattern and multiply that times a virtual table, this is still an adapter, but you ask a middle tier layer for, give me an adapter that knows how to talk to some virtual abstract adaptee interface. This one knows how to talk to this particular type, and it goes off and it talks polymorphically to this. There could be multiple of these that some derived layer, not derived, some further layer gives back. This guy knows how to translate it for you. This guy knows how to translate for some other type of interface. So this is a basic adapter, but with some polymorphic mechanisms in it. This isn't actually part of the original definition of a design pattern. This is using the whole idea of the abstract concrete implementations of doing things polymorphically and multiplying and adding it. And a lot of times you can take a lot of different patterns and use one inside of another, or to extend the concept to how a lot of others are. And you'll build your own toolbox out of Lego blocks. When you're a kid, you get the Lego blocks, you stick two of them together, and you say you built something. But now you can take that one widget that you just built and you build bigger things out of it by sticking multiple widgets together. That's what design patterns are and how you can mix them. Sometimes using design patterns inside of other design patterns to extend them makes things really complicated and goes counter to having them work together. If that's the case, that becomes an anti-pattern. If it becomes complex, you're doing the wrong thing. A decorator, I got multiple slides for describing this one because it doesn't really read the way it is. The daisy chain of operations we had down, where we pass it from one to the next, that's what we're doing here. We're making one component, we're passing that into another component, we're going to be decorating it, we pass that into another decorator. As each of these calls down through the chain of the pipes of what it's passing through, each one's going to be massaging the data or doing something different. I know the print is small on here, that doesn't matter, but what this is doing here is this is doing something before the operation is called, passing it on to the next guy. This one's doing it after. So this is massaging the data going in, this is massaging the data coming out. A more specific view of this, so you can see the relationship. Oh, something I may not have said, and I think you may have figured this out. This is a base class. This is an intermediary class that derives from this. These are further derived that derive from these. So we have we got a generic decorator, and we have a concrete decorator. They do specific implementations. One way they're looking at this higher or more of memory model, how it fits in memory, is when you derive for something, you actually have classes inside of your classes. So we have our base interface, and we have our component that then we further derive from, we have our decorator that we further derive from, we have our outer object. As this guy goes to call in, all it's doing is drilling down, and the base class knows who is next in the pipeline. So he does his operation, does the thing, and calls down and say, pass this on to the next guy in the chain. He throws back up, does a virtual, yada, yada, and it becomes the pipeline. One of these, you can actually visually look at one of these along the way. One pipeline type of chaining that you may have seen before, the GStream, which is actually implemented in C, is a multimedia streaming toolbox where you can say, I want to have a data source that's pulling my data from this file or this network connection. And I'm going to run it through a decryption. I'm going to run it through some filters that apply a fuzzy to the image. And then I'm going to just run it out to some other final filter that's a data sync that displays it. These are objects which are chained together and they pass along. This may look a whole lot like the previous implementation that we saw of where we have the middle layers and the virtuals and the derived. This one is a abstract interface, it's a concept of how it knows to do something. You've probably heard this better under an impl. This object has interfaces that can pass off, and this is actually how do we implement this function, and this is how we implement this function. Their implementations are done different, but you have generic interfaces to talk to those. So databases, you're talking to one particular Microsoft SQL server, or you're talking to some other database. They all speak SQL, they speak slightly different versions, so your implementation of those connectors is going to work differently. That's how it's done here. It's an actual implementation of how it's done. Or buttons on a UI. You're on Linux, your button works a certain particular way, you have to create it special ways. Windows, a button has a lot of the same features, but it works differently. But you don't care what your application says, I just need a button that does this. You would implement it specific to that platform, and your abstraction hides all that difference from you. Now, the proxy we talked about of you, and then this particular example saying it checks the authentication. First time through, it authenticates and stores that token for you, and then later it makes sure you're authenticated. If it came back the first time and said not authenticated, you get an error. It's just going to keep returning back saying, authorization failed, not working, not working. Or if authorization works, it sends the request through to your database or whatever where you say your password through. And notice again, the symmetry of a lot of the patterns. If you got something in the middle, this is really an adapter pattern that hooks it on the way through and says, do we want to interfere with how our connection is going to work? And then it passes the data through. Instead of an authentication, this could have actually been a caching mechanism saying, it's really expensive to send this across the wire. I'm actually going to have to put this in a letter and mail it, and it's going to go on the Pony Express and take a long time to get across the country. So you save up 4 or 5 of these things, and whenever your buffer gets full, then you say, then I'm gonna write it across. And then so then it does the request only once your buffer's full. And it returns immediately, and it doesn't know that it wasn't sent, it just thinks that it was. And so this proxy gets in the way, or handles what this guy, what your original source code was actually wanting to do. Flyweight is that example where I talked about you have an expensive operation to do, and so you created originally with whatever parameters you needed. You created one of these flyweight objects, and it stores it away in a cache, or your application maybe remembers it. But then you're saying, I'm gonna want to use my flyweight object 1 and pass the parameter 10 through. And so then it's gonna use your virtual mechanism on the pre-constructed object, pass in the 10, and it's gonna do whatever with that 10 that you wanted. And then I've also created a flyweight object 2, with some of these, and then actually I have a object named flyweight object 3, but it's just yet another copy of object 1. It grabs it out of its local cache of objects, and so you have both flyweight 1 and flyweight 3, which are pointing to the same object, but it's saying I can treat them as 2 separate instances. This could be different parts of your program that each have this, and this flyweight 3 is saying I'm going to pass the 30 through, and flyweight 1, it says I'm going to pass the 10 through, and it's stateless. Your object has state, but as far as this API is concerned, it's stateless. You didn't change anything in the object. It's just passing it through to whoever is consuming that it's going to do something with. So here, the operation had that extra state, the value that's getting passed through. It's using it and munging. It knew what its original internal state was when it was constructed, and then the external state of what the parameters were this time, and it did whatever it needed to do to munge them to do that. Didn't change the internal flyweight object itself. I only clicked once there, didn't I? Good. Yeah. Facade, oops, oh. Too many buttons, I got 2 buttons, so forward and back, and I can't run them. Facade is, you have these 3 different objects. They're doing these different operations, and you're saying, I want a single API that I can call to simplify to do these operations in these steps. And I say, do operation ABC. And it calls each of these subordinate objects that are contained within here, could be considered a composite of these things, and do these things and do them in this order. And this is kind of a variation on it. Just for example's sake, I added a second operation of an AC that only calls and does certain operations with subsystem A and subsystem C. And so it calls just those. It's an outside API where I didn't actually have to create here locally subsystem A, subsystem B, subsystem C, and then call each of them and do each of the stuff. All those mechanical steps are abstracted and hidden away behind this facade. Facade is like the front of a building that's the false front on it. Doesn't matter if it's a bank behind it or a video store or whatever, it's just a fake front on it. And it knows how to do its stuff internally. Composite, this isn't what you think of a composite of a normal class that has a bunch of other members. This is a collection on the fly where you're gonna say, I'm gonna make this collection and I'm gonna add a bunch of these different leaf nodes to it, and then I'm gonna apply this operation across the entire thing. This is a simplified example. Rather than being a leaf object, I could have actually had a branch object that I added in there, was derived off the same base interface, and it could have been an entire tree of branching out, and then leaf on the terminal nodes of it. And then when I say this do operation, it would visit every branch in the tree and apply that operation hierarchically through that. So it creates this one interface, this composite interface, that I can apply all these actions to of all these things that were stored in that tree. Here again, design patterns are extending each other to make new names, make it more complicated. So so it's yet more secret code inside of secret codes. Requires a separate second handshake for that. Okay, behavioral. This is how objects internally think and get things done when they don't care necessarily about how other modules are doing their thing. It's just saying, rather than the relationship between modules, I am just this module, and this is how I'm going to do something internally, and I'm going to expose an API, and people can call me to do whatever. We went through this list before. We'll hit each of these. And again, more adjectives. Extensible, decoupling, flexibility, maintainability, modularity, performance. Sound familiar? And actually, the one that's a little different on this is decoupling. Rather than separating interfaces, this one is the other people don't need to know about my internal implementation. I'm decoupled from the outside world. This one is a transactional. You're gonna set up and I'm gonna execute a bunch of command objects and store them away. And so you say add this command, and then I'm gonna say execute. So this is all, you're dealing with a database. And you say do this action, do this action, do this action, commit. So this is the object version of a database transaction, commit. And it might be that the execute actually does call the database and apply each of these commands and do a commit there. Chain of responsibility is the daisy chain piping things along, but each node in that daisy chain knows how to handle very specific situation and commands. So you passing down from your main object, you say, I know I have this chain of objects and they know how to handle situations, and I'm gonna pass through this command of do this, and it passes it through this whole series of daisy chains until it finds one that says, I know how to handle it, until it gets all the way to the end, it says unable to handle request. You would use this potentially in a situation where each different filter knew how to handle a specific type of error message. And you execute a command and it comes back with an error message, and each filter would say, I know what that error is, I'm gonna do with it and return what I want. I'm gonna actually process how that error message is supposed to be handled. Either I'm gonna log it, or I'm gonna cause an exception or do something like that, or throw different types of exceptions. And if it doesn't do anything with it, say, I don't know what that command is, that error message coming back up, that throws it up to the next filter, and he says, I know how to handle that error message, I'll do it, or I don't, and passes it along until it gets all the way back up, and it finally gets to the end of the chain saying, I don't know what to do with this at all, I'm just gonna throw a general exception, and my program's gonna crap out and terminate. Shouldn't do that. But so each node it's a chain, and each one has its own responsibility of what it's supposed to process. Here again, that daisy chain of each step knows how to handle something and can return it back up or massage the data and pass it through. Could be your error message is string too long, and your handler knows to say, well, just truncate the string and pass it through again. Or it could be actually pass a hard error saying, username, emailed, there's no @ in the email name. And a different part of it would check that it's an actually valid domain that it's trying to email to. Whenever I sign up for spam of something or someone demands an email address from me and I don't want to give it to them, I do noyb@noyb.noyb. It has the ats in it, and the noyb is none of your business. So if I start getting spam from that, I'll know it was one of you guys. Interpreter, here's the one I talked about. I build up a hierarchy of an addition and subtraction where it evaluates a variable and I have a constant. This is a tree. And so I build up this, I set the context of what the variables are, X and Y's, 10 and 5, and I tell it to interpret it. And it goes through and hierarchically traverses through the tree, evaluates it, and spits out the answer. This is the example that potentially more of you wrap a regex expression engine and say, this is my expression, this is my string I'm passing in, evaluate. And it applies its regex rules and it returns you the list of parameters that it found that matches your regex expression that you passed in. And then you can pass it a different string and apply that same regex expression to it. It's a language inside of your language. It could be an SQL. You pass it in a generic SQL and it transforms your generic SQL to something particular that Microsoft SQL can handle versus maybe even translate it into a NoSQL database command, or even 2 or 3 different types of SQL, because each different server handles different SQL, the same SQL command differently. You can or can't have different levels of nested wheres and whatnot. And I'm not a database guy. I had to do it once, and I forgot it promptly. So this is an object that knows how to implement its own object. If you wanted to, you could actually do a Python parser inside of a C++, pass it a Python code, tell it to execute it, and it would do its digesting and spit it back out. You know, it could be whatever you want to wrap in there. Iterator, when these were originally written, C++ did not have iterators. Iterators kind of slowly snuck in latter 90s as more of the STL came around. STL wasn't originally part of the language. Sun came out with STL port, which standard template library, which then slowly got released to the public, taken over and maintained by HP, which then got turned into the standard template library we know now, where we had iterators back when you do a collection begin and collection end. But prior to that, people had the same need for saying, I have this big blob array of data and I don't care how it's implemented. I need to be able to say, is there a next node in there? Give me the next one. Is there a next? Give me the next. And so it iterates through this data. It's a general concept of how you would potentially iterate through something without knowing what it is. Same with exactly what we do with iterators now. You might use something like this if you had a file system with a whole bunch of files in it. You can't actually ask a file system for an iterator of all the different files for it. The implementation knows how to get at the next file in the list. So this where you just basically say, is there another file? Is there another file? You know, get next, get next, get next. And because of the logic we have now for iterators, you always just test the iterator to see is equal to end. In old days, you had to say, is there another one? If there is, then give it to me. You just can't say, give me the next one and depend on it to fail. State, this is the state machine. Many times state machines are mentioned are implemented with switch statements. Switch statement has the current state that it's in, but it's got a verb or event that comes into it. It says, okay, I'm in state 27 and it's telling me to reset the connection. But if you were in state number 1, it's going to say, you send the event through to reset the connection. So I don't know how to do that. I haven't established a connection yet. So sure you've all seen the different state diagrams, lots of different bubbles with lines drawn between them and loops back, depending on what's happening in different states. That's basically, a state is an object that has a state. It's a state machine. This one is a really weird state machine that each step through it, it gets dispatched off to a derived object, and this object says, I know how to handle this event. That argument is, in this case, I know I can mod 2 with it, and then I'm going to dispatch it off to a new object called state 2, and that gets assigned, when I say makes set state, it actually makes one of these objects, assigns it to my current state, so the next time through, the event will be sent to this object, and at that point, it's going to say state 2, it's going to do a mod 3 on the argument. And actually, I got a typo here. I said event here, but and I said arg. There should be the same. So if it's an event mod 3, I'm going to send it off back to state 1. If for some reason I ended up in a state 3, I'm also going to go back. I think my slide's wrong there. This should be, if it's not a state 3 or a mod 3, see I make a state 1 there, it would fall through and construct a state 3. This Godbolt slide will have the code more correct. So rather than actually having a switch statement that knows how to handle every different event and every different state, the object that gets created here says, I only know how to handle the objects for my state that I'm in now. It gets an event, it decides how it wants to handle it. Any that it doesn't, it would say, I'm just not gonna handle it and return an error. Exactly what your switch statement would do, but your switch statement is all written out, compounded together. That generally, state means any type of state machine. This guy, it could be state 1, state 2, and state 3 are in completely different modules that don't really know much anything about each other except for how to get to the next state. There could be 99 different states. State 1 only knows about states 1 and 2. State 2 only knows about 2 and 3. So you get some sort of state 4 that you've created and it ends up in here. It may create state 99. These guys don't care what state 99 is, but polymorphically, it's stored away in what the current state is, and it knows how to handle itself. So by adding more modules to your program, it can dynamically change the flow of your program of how the state machine is going to operate without affecting all the other states. It knows how to handle its state. So you don't have to recompile your base implementation of your whole dispatcher to know what the events are that it's going to handle. Just whatever, could be say some sort of file or you have a plug-in extension that you plug into your application, and it loads a bunch of its own states, and it knows how to do its own processing. Observer it's a publish subscribe where all the people who subscribe to it, the newspaper, when they publish their want ad in there, could be, in the personal section, middle-aged, gray-haired, bearded guy seeking whatever, everybody gets that notice. And these people can attach themselves or remove themselves from the list at any time. You can cancel your subscription to the newspaper going, I don't want to see any more ads from a white guy, middle-aged with a beard. So I don't want to hear about that anymore. So then the next time the ad comes out, the guy that detached himself from it isn't gonna see that same ad again. Okay. My font got clobbered off the top there. This is the moderator pattern. It's just like Observer, but I don't see my own ad in the newspaper. If I have a chat program, if I send a message out, I don't need to know what I said. I already know what I said before I sent it. A lot of confusing arrows here. You don't necessarily need to follow all of them. It's just the idea of that messages, you add colleagues and you send out the message. It could be publish, subscribe. The examples I happen to have found for this, typically they added themselves in and then they never removed themselves. In theory, you could remove yourself. There's no reason why you can't extend this pattern to do that. You about to ask a question there? You look like you had it. Oh, okay. Memento. If you know your Latin, memento means to remember. Tempus fugit, memento mori. Time flies, remember death. So memento. This is undo. You go, a lot of squiggly spaghetti here, but basically you have a document object, you set the state in it, you set the state, you say add state. It's taking a snapshot and it adds it to a undo buffer. And you do set state, you remember the state, you set another state. Then you can go back and say, get the state at save point 1 or save point 2 or whatever mechanism you used, and you can play it back and forth and see what the old states of the document were, the new state. Get. You can go back and see what this particular branch was at this point, and do a diff between them if you wanted. And basically this is actually remembering, checking, and saving away what the actual variable state was when it stores it away. It could have just as easily gone out and cloned the entire document and saved that in some sort of undo buffer. So it's depending on what you want to do of saving each particular operation or not. Another useful way of using memento is a hooking mechanism for recording macros. You do a series of operations, you remember, figure out what those operations were, and you save a snapshot of those operations away. So you can go back and replay them later. Strategy is you have a set of objects and you want to apply a strategy to them. And you use those same objects later, you want to apply a different strategy. This is the encrypting a file or encrypting a socket communication. You set this strategy of you want plain text. And you say execute, send all this stuff across. And you say, oops, we got some sensitive information come through. We're gonna set the strategy for encrypting the data. And then you do execute. And the data that you're sending at that point is using this strategy object that we set, which is passing it through an encryption filter of some sort. Probably lots of other uses you could use for it too, but that's something that's a real world useful potential example. Or actually, if you're dealing with a server and all of a sudden you ask that server, which types of encryption do you know? It's this type or this type. You can switch which one you're using and say, I'm gonna talk to you in your language. Template method is a little bit like a facade, a little bit like that example with the pizza baker of you have a couple derived classes that know how to do all these different steps. But in your base, you say, I'm gonna want you to do these operations, and it's gonna do all these subordinate operations. And here I say odd, we're gonna do steps 1 and 3. We're gonna do the evens. We're gonna do 2 and 4. We're gonna have another step, and I'm just picked these arbitrarily just so they would be different. It's gonna be prime numbers. It's gonna do 1, 2, and 3. And it calls the virtual methods of steps, 1, 2, 3, or 4, depending on what this template told it to do, and it's gonna do all those steps, of 1 and 3 or 2 and 4 based on which operation it was told to do across these whole set of things. So there's some usefulness in that of a virtual mechanism on the facade, if you want to call it that. Now, visitor, this is hierarchically climbing through a tree where you pass the same operation to every element in the tree. I use the example of an output streaming object of where you're basically giving it a C out. You could have just as easily given it any streaming object and spit text out to it. It could be a file stream that satisfied an output stream, and you're sending these across the wire. So you would climb the whole thing. I used it once in I had a massive document object that could contain any sets of amount of data in them, and I wanted to save that out to disk. As I had an archive object that I would pass down to each object, and each object would call its subordinates objects and say, store yourself away in this archive object, and it would go hierarchically through the whole tree, saving itself out. Then I could later read it back in, and this breaks really what visitor was. It's almost the inverse of visitor, of as I was streaming through my archive, I would say, I know the next object is gonna be one of these, or one of these. So I would create them on the fly and then read the data back into it. That's not visitor, it's kind of counter visitor. But that's one place where you might use something like that. An interview question I had once given to me was, you have these strings or series of numbers, which are node identifiers in a tree. And then when you traverse through the tree, when you do it in order, it does left, me, right. Me in the node I'm at in the middle. So it traverses through the tree, goes left, 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 prints me out, reverses back up, prints me out, goes down the right branch until it gets the next node, and it says left, 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 right, and then it prints me, prints me, prints me, as it's winding back up, then left. And so in order, in this tree, if you were to print this out, is 3, 5, 6, 7, yada, yada, yada. Post order, if you print yourself out last, it's me, right, left. So you go left, 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 do all the rights, and then me at the end. The number stream looks like 3, 7, 6, 10, yada, yada. Knowing just those numbers, reconstruct what the tree looked like and spit out the pre-order of, if you put me first, you print out me, then you go down the left branch and the right branch. So this is a more full-blown templatized version of what I had done for the solution for that. So you have your in order, your post order. I would say rebuild tree. It would go through, from this, it would know how to rebuild the tree. I had a tree diagram, then say, okay, now print out the pre-order list of the tree so we can verify that against the way we knew it was gonna be. So I took my tree object, and this is above and beyond, not part of the visitor, but you might find it useful. It's a functor, basically a class that takes a parameter that once it lives in it, immediately is evaluated. So I created this class that takes a tree, then it gets called by the streaming operator and asks it to stream itself out. And what I would do is this streaming operator, I knew that I was coming from a pre-order object. I would call the node and tell it, spit yourself out in pre-order order. So do the output stream spit out the this and a comma, then I'll go down the left branch and then the right branch, going recursively down, pre-order, pre-order, pre-order. So not only was I recursively climbing through the tree in a different order, then I asked the tree, the object I was passing through that I was visiting upon each node was this output stream. I'd ask each node, just spit yourself out, and it would spit out what it was. And so the actual implementation that I did for this, I actually have 3 different functor objects. One is a pre-order, one's an in-order, one's a post-order. So I'm given the in-order and the post-order, and I would spit all 3 out. And you'll see that in this Godbolt example. It, just to kind of, it's not complicating showing extra ways you can use this of doing the functor object to say the same representation of streaming it out and viewing it in different views, and visiting the tree, kind of in the same order, but outputting the nodes in different orders, if that makes any sense. Then, so my example spits out all 3 by traversing the tree different ways, and you could check to see that it made sense, that what these outputs are. So now that you know all these different patterns, you can basically take them, build what you want, combine them. You don't want it to look like an Escher diagram, though, where you don't know which way is up, because that's an anti-pattern. It just boggles the mind to try and look at an Escher diagram and figure out what it's really doing. Any questions? Did I do a good job of explaining everything? Was it too basic, or did I baffle you at the beginning and no one wants to say anything? Go ahead. Or there's a microphone around here someplace that if anybody has questions, they should speak to the microphone. Oh, you were just smirking at me because we had drinks last night. Yeah, okay. He said he was going to ask questions. So. Back there, you need.
Just explain again when the state pattern is used. What is its use?
The state model?
Yes.
Well, that is basically the typical model of a state machine would be something like you had a communications module, and it had a switch statements in it of where it knew that if it was in a connected state and what data it was busy sending across. The example that I showed here, which was a really weird, far-flung, would be you had a program that only knew how to basically said it knew that your object was going to have state and that you were going to dispatch commands off to it. But you loaded some plugin extension or several of them to your application. And your application, each one of those plugin modules would say, I'm at this state, I know my next state is going to be on. I'm at 99, it's going to be 99B. So you could actually construct that plugin would handle a 99B object, and then pass it back and say, this is what your current state is. Next time it went through to do the dispatch, it would be sent to that 99B object that's in the plugin. Your application doesn't know at all what that is, but it's provided the code for you to handle that. It's a really far-flung example, which I have never actually seen used in the wild. It's just the idea of you can extend a state machine without adding extra switch statements in your main line. How are we doing time-wise? We're at time? I timed that perfectly. The 50 or 67 slides in 90 or 80 some minutes. So no more questions. Or people have questions and they just want to hit me afterwards because they don't want to say them in front of everybody, I'll be available. So thank you.